What follows is what one might call a static video. No equations will be written in real time, and no MATLAB commands will be evaluated. Instead, what follows is a narration of the contents of a PDF document designed to give you a broad perspective on second-order linear ordinary differential equations, explain our approach to solving them, and introduce you to the specific techniques we will use to do so. Okay, so here we go. So this video is intended to identify the overall strategy and specific methods which you will learn in this course for solving second-order linear ordinary differential equations. The video presents an overview and shows how the very general question of finding all solutions to such an equation boils down to two specific problems. It then indicates the techniques you will use to work those two problems, albeit only under some fairly general but still special circumstances. You will learn the concrete methods to apply to the two problems later. Here we only name them and describe how, having eventually solved those two problems, you can then solve a general second-order linear equation. So, a general second-order linear ordinary differential equation is a differential equation of this form: a of t y double prime plus bt y prime plus c of t y equals d of t, where y is an unknown function of t and a, b, c, and d are given continuous functions on some fixed interval, which we'll call I. And we note that the interval could be infinite in length. It could be the whole real line or the positive real axis. The equation star is clearly linear in y and its derivatives, thus the name. A solution of this differential equation is a twice differentiable function, y equal phi of t, defined on the interval so that it solves the equation. If you put phi of t in, you get the same thing on both sides. A related initial value problem, or what we sometimes call an IVP, would be a combination of the differential equation together with two pieces of initial data given at some point. So the value of the function and its first derivative at some point in the interval. Before we state the fundamental existence and uniqueness theorem that obtains here, we'll normalize the equation by dividing by a of t. So we're going to divide out the a of t. Well, the zeros of that function may cause some difficulties, and so to avoid them, you may have to shrink the interval somewhat. And after you do that, it's common to change the notation. We typically use a notation like this: y double prime plus p of t y prime plus q of t y equals r of t. Again, p, q, and r are continuous functions on some specific interval, and we want to solve the equation. We will make use of the fundamental existence and uniqueness theorem. It states that for any value t0 in the interval, if you specify two real numbers, y0 and y0 prime, then there exists exactly one function, y equal phi of t, that satisfies both the differential equation, for all t in the interval of course, and the initial data. Next, the equation is called homogeneous if r, the right-hand side, is identically 0, and inhomogeneous otherwise. So we'll consider homogeneous equations first. So there's our typical homogeneous equation, linear of course. The right-hand side is 0. Well, the basic fact about homogeneous equations is the following. If you consider the solution space, so the set of all functions twice differentiable on the interval I, which satisfy the homogeneous equation, the claim is that is in fact a two-dimensional vector space. What does that mean? It means that if you have any two elements in there, that is any two solutions, then their sum is a solution. It also means that if you have any solution and you take any real number, then the product of the real number times the solution is, again, a solution. So that's what it means to be a vector space. And they can't be any two. They have to be linearly independent solutions. So phi1 and phi1 and phi2 are linearly independent, meaning that neither one is a multiple of the other. And to say that the solution space is two-dimensional means that they span the whole space. That is, any solution is a linear combination of the two linearly independent ones. So that's what it means to say that the solution space is two-dimensional. Both phi1 and phi2 are non-zero. Neither is a multiple of the other, and every solution function is a linear combination of these two. Now, there is actually no unique choice of phi1 and phi2, but given a point in the interval, there is a canonical choice. In fact, by the existence and uniqueness theorem, you can pick out two specific solutions, phi1 and phi2, which satisfy these pair of initial data. The first one takes the value 1 at the data point t0, but its derivative is 0. And the second solution does the reverse. Its value at t0 is 0, but its first derivative takes the value 1. Now, it's clear that those two functions are linearly independent. Either one could be a multiple of the other unless they were both 0, but they can't be 0 because of this condition here. But that fact also follows from a special test that you will learn, which I want to mention here, namely, given any two solutions, phi and psi, you can form what's called their Wronskian, W phi psi, and the definition of it is that it's just the product of the first times the derivative of the second minus the product of the derivative of the first times the second. Facts that you will learn about the Wronskian are that it's either identically 0 or never 0, and that two solutions are linearly independent exactly when their Wronskian is not 0. So if you compute the Wronskian of the two functions phi1 and phi2 constructed here, it's obvious that when you evaluate this expression for those two functions, you get exactly 1 at the value t0, so it's not identically 0, and so those two are linearly independent. Okay, so to find all solutions of a homogeneous equation, you only need to find two linearly independent ones. Then any other solution will be a linear combination of those. But here's the amazing fact. In fact, you only need to find one solution because of the so-called method of reduction of order, which you will also learn. And I'm going to specify what the method of reduction of order says. It says, given a linear, homogeneous, second-order ordinary differential equation, usual expression, and if you have one non-zero solution of this equation, say y1, then you can obtain a second linearly independent one, by setting y2 to be a function u of t, which you don't know yet, times phi of t. So u of t is an unknown function of t. Substituting into the differential equation and evaluating all the terms, you have to do a little algebra, but after you do that, you see what drops out is a first-order ODE in the function u prime. Linear. So first-order linear equations, you learned how to solve those in the first third of the course. So you solve for u prime, you anti-differentiate it to get u, and then you multiply by phi. And that gets you a second linearly independent solution. Since u is an antiderivative, it can't be constant, and so y2 is not a constant multiple of y1. And so you've actually produced a second linearly independent solution. That's the method of reduction of order. So we have now reached the first of the two basic problems to be described in this video. We can now state it. Problem 1, given a homogeneous, normalized, second order, linear, ordinary differential equation. So there it is. Homogeneous, second order, linear, homogeneous differential equation. The problem is find one non-zero solution. If you can, then you can find all solutions. First, by using the method of reduction of order to get a second linearly independent solution, and then observing that any other solution is a linear combination of the two you have in hand. Well, we'll comment below on whether and how we can actually solve problem 1. The second problem arises when we pass to inhomogeneous equations. So now I'm allowing the right-hand side to be non-zero. We have now an inhomogeneous equation. Here's the key observation. If y1 and y2 are both solutions of the inhomogeneous equation, then by the linearity, the difference of those two functions is in fact the solution of the homogeneous equation. That's easy to see. You plug y1 in, plug y2 in, subtract the two equations, the r's go out on the right-hand side, and you get this assertion that the difference of two solutions of the inhomogeneous equation is a solution of the homogeneous equation. It follows immediately that if you specify a particular solution of the inhomogeneous equation, then every solution of the inhomogeneous equation is just a sum of two functions, one of which is the particular solution you have, and the other is any solution of the homogeneous equation. It's kind of evident, but conversely, if y1 is a solution of the homogeneous equation, then if you add it to any particular solution of the inhomogeneous equation, again, you get a solution of the inhomogeneous equation. And so this gives rise to our second problem. Given an inhomogeneous, normalized, second order, linear, ordinary differential equation in this form, all we need to do is find one particular solution of that equation. So we can now summarize. If you can, then you can find all solutions, provided, as a consequence of problem 1, that you can find one solution of the associated homogeneous equation. In summary, given an inhomogeneous equation, if you can produce one non-zero solution of the homogeneous equation and one particular solution of the inhomogeneous equation, then you can find all solutions of both equations. Now, when can you solve problem 1? The answer forms much of the content of the middle part of the course. Here are some of the instances that you will actually study. 1. When the coefficient functions p and q are constant. Second, so-called order equations, which in the context of the original formulation of an inhomogeneous problem, that's when the coefficients take this form. So it's when you have an equation in which the coefficient functions are monomial, and the degree of the monomial matches the degree of the derivative in any particular term. And the third instance is some special equations, which we will typically are solved by the method of series solutions, and they give rise to special functions. You'll see some of those in this course. Examples are Bessel's equation, Airy's equation, or the Legendre equation. And for more on that, you can actually see the MATLAB presentation called Second Order Linear Equations and the Airy Function, which you can find in the internal links of Chapter 2.2 in the notes. Finally, when can you solve problem 2? Well, the cases you will encounter include 1, when p and q are constant, and when the non-zero right-hand side is of the following form. It's a finite linear combination of products of exponentials times sinusoidals times polynomials. When that's the case, you can employ the so-called method of undetermined coefficients. You can always apply the method of variation of parameters, provided you can solve problem 1. The answer you get when you do that will be expressed in terms of antiderivatives, which you may not be able to evaluate in terms of elementary functions. Sometimes you can, sometimes you can't. A third example is when p and q are p and q are constant, and r is expressed as it was in the first one, this kind of finite combination, but with each term multiplied by a Heaviside function. So you wind up with discontinuous forcing term on the right-hand side, and that's the case where you apply the Laplace transform technique. Okay, so hopefully this organizational review puts all the topics you will study when investigating second-order linear ODEs into a perspective that will enable you to see how they fit together. Let me just summarize by saying that there really are three major topics in this course: first-order equations, second-order equations, and also higher order, but we concentrate on second. And the third is systems. And what I've done in this video is to try to give you a framework for all of the topics that arise when we study second order equations.